Next is the application of first law of thermodynamics. The mode of transfer of energy between system and surroundings happens in two different ways. That is, the exchange of energy between the system and the surroundings can occur in two different ways. Heat and work are the two important modes of transference of energy between system and surroundings. The mode of transfer of energy between system and surroundings happens due to the difference in temperature. So the transference of energy takes place as heat if the system and the surroundings are at different temperatures. We all know that. The exchange of heat occurs through the thermally conducting walls which constitute the boundary between system and surroundings. If the system is at higher temperature, the energy is lost to the surroundings as heat, causing a fall in the temperature of the system. The energy transfer continues till the system and the surroundings attains the same temperature. If you're taking a hot cup of coffee, after some time what will happen? The coffee is at a higher temperature. It will escape to the surroundings. This happens till both system and surroundings is attaining the same temperature. Now, if the system is at lower temperature than the surroundings, then the energy is gained by the system from the surroundings. That is, the heat flow will take place from the surroundings to the system till it becomes equal. So this is the basic thing that we all know. So the one mode of transfer of energy is heat. The exchange of energy between system and surroundings can occur in the form of work also. The work can be mechanical work, pressure volume work, or electrical work. So here the mode of transfer of energy between system and surroundings it takes place in the form of work if the system and surrounding is at different pressure. That is, you can imagine a piston where the piston expansion is taking place. So the expansion is taking place. Why? Because the internal pressure is actually less than the external pressure. So there the expansion can take place. So compression will take place when the external pressure is greater than the internal pressure. So the piston will move downwards. So when the system and the surroundings are at different pressure, then the exchange of energy will occur in the form of work. What is the sign convention of heat? So according to the international convention, heat absorbed or evolved is denoted by the symbol Q. Q is positive when the heat is absorbed. That is, heat absorbed by the system is always positive. It is taken as positive, as Q will be greater than 0. This is very important point while doing problems. Q is negative, that is, heat given out by the system is negative when the heat is evolved. That is, heat given out by the system will always be negative, means Q will be less than 0. Now what about work? The work done on the system is positive. Work done on the system is taken as positive, and the work done by the system is taken as negative. That is, W will be less than 0. So these two important points are very important when we'll be doing problems. Expansion work is negative. That is, during expansion, the work is done by the system. Isn't it? That is, it is the gas. Imagine a gas taken, as I've told you earlier, taken in a cylinder with a movable piston. If the piston is moving up, means the gas is undergoing expansion. So during expansion, the work is taken as negative. And if the piston is moving downwards, means work is done on the system. That is contraction work, and contraction work is positive. From the first law of thermodynamics, we have the change in internal energy delta U is equal to Q plus W. Now, if Q is equal to 0, means there is no heat energy absorbed or released, then delta U is equal to W. if the work done, if there is no work done, W is equal to 0, then delta U will be equal to Q. This is the basic thing that we can understand very easily. Calculation of work. That is, we have actually two different forms of work. The common forms of work that we come across in the study of thermodynamics are pressure, volume work and electrical work. So in thermodynamics, the pressure volume work is very important. This type of work is also called the expansion work and is significant in systems which consist of gases and involve changes in the volume against the external pressure. So we are going to derive the expression for PV work, expression for pressure volume work. So how are we going to derive it? Consider here a piston. A movable piston is there and it is in a cylinder. The cylinder is fitted with a movable piston. So cylinder with piston containing 1 mole of an ideal gas is taken inside. Total volume of the gas is VI. That is the initial volume. I for initial volume. Pressure of gas inside is called the internal pressure. And external pressure is above, which is being applied on the piston. That will take it as PEX. It is external pressure. Now we can plot a graph V volume against P, which you have learnt in states of matter, the Boyle's law, pressure and volume. We know, as I have explained in the states of matter also, you can see in the diagram there, we are going to apply pressure. So when applying pressure, what happens? The volume is decreasing and this is the final pressure here. So here actually the work is done on the system. Compression is taking place. So as pressure is increasing, what is happening? As pressure is increasing, the volume is decreasing. From the graph it is very clear here. You can see here the initial volume. And as the pressure is increasing, the graph is going like this and you get the final volume. And you can see the displacement here. That is, the piston is moving through a small distance L, which is shown here. Length of the piston moved is L. Final volume is shown here. After compression, the volume is decreasing. The area is actually external pressure into the change in volume. The area shown here is the external pressure which is above the piston into the change. What is the change in volume? It is the V final minus V initial. Final volume is less, initial volume is greater, children. So it is delta V is equal to V final minus V initial. Delta V is the change in volume, or that is equal to L into area, where L is the distance of the piston moved and A is the area of cross section. A is the area of cross section. We know pressure is equal to force by area, or force is equal to external pressure into the area. Now we know W, the work of expansion, is equal to force into distance or displacement. What is the displacement here? The displacement is L. So we can write it as force we know is external pressure into area. Substituting the value of force there, expression of force here in W, the work done, you get W is equal to external pressure into A. We are writing that, and distance moved is L. So W is equal to external pressure into area into L. Or W is equal to P into minus delta V. Why minus delta V? Because the final volume is less than the initial volume. That is equal to minus P P delta V, the negative sign of this expression is actually compression. That is A into L, which was earlier, area into the distance moved, refers to the change in volume delta V, and that is why external pressure into area into L, the AL term is taken as a change in volume delta V, and that is why W is equal to minus P delta V, and this is for compression. If the pressure is not constant at every stage of compression but changes in n number of finites, that is, this expression that we have learnt now, W is equal to minus P delta V, is for an irreversible process. For a reversible process, in each step there is equilibrium is being attained. That is, the compression or the expansion takes place in an infinite number of steps, which I have earlier explained the difference between a reversible and an irreversible. So here this sentence is about the irreversible work done in an reversible expansion of an ideal gas is what we are going to discuss now. For overall change, it is taking place in minute infinite number of steps. So from initial to final, you can find here you have to integrate from V initial, work done expression for a reversible expansion of gases. You have to integrate between V initial and V final into Px into dV. And on integrating it, under reversible condition, we relate the work done term to the internal pressure. That is, on integrating, external pressure is internal pressure plus a small change in pressure. That would be the external pressure. So we are expanding the external pressure as internal pressure plus small dP, the small change in pressure, into dV, or internal pressure into dV plus dP into dV, and dP and dV are very, very small, so it can be ignored. So the work done for a reversible expansion of an ideal gas is integrating between V initial and V final of P internal dV. We know that PV is equal to nRT, or P is equal to nRT by V, or work is equal to integrating, writing the expression for P as nRT into dV by V, or you can write it as minus nRT log V final by V initial. It is V final by V initial. That is, integrating 1 by V dV is log of V final by V initial, which you'll be learning next year in mathematics, differentiation and integration. So converting it into the common log, it is minus 2.303 nRT log to the base 10 V final by V initial. So this is the expression for the work done in an isothermal reversible expansion of an ideal gas. Now, expansion of a gas during the expansion of a gas in vacuum, the external pressure is equal to 0. So P external into delta V would be equal to 0. Delta V is equal to 0, or delta U is equal to Q minus P delta V. Because why it is Q minus P delta V? Because for the expansion we have learned W is equal to P minus P delta V. For during expansion, the work is done by the system. Isn't it? The earlier expression for PV work, the work done by the system, that is V final minus V initial, would be equal to 0, because during expansion the final would be greater. Therefore, in order to satisfy the sign convention, we put a negative sign in front of the expression for work. So whether it is expansion or compression, W is equal to minus P delta V. So that is what we have learnt earlier. So delta U is equal to Q plus W, or work done is minus P delta V. So work expression is written as minus P delta V, or delta U is equal to QV. That is, What is internal energy? Internal energy is the heat evolved or absorbed in a reaction at constant temperature and constant volume. That is, when the volume is kept constant, whatever energy is taking place, the change in internal energy is actually the heat evolved or absorbed at constant temperature and constant volume. But we know most of the laboratory reactions that we do in the lab, the volume is kept open. That is, there is a change in volume when it is conducted in the laboratories. So that energy is not called internal energy, that is called the enthalpy. So enthalpy change is actually the change in internal energy taking place at constant temperature and pressure, while internal energy change is the heat change taking place at constant temperature and volume. So this is the basic difference between enthalpy and internal energy.